Welcome to another exciting episode of Algorithm Analysis and Design. I'm your host and your professor, Dr. John Baugh. In this lecture, we're going to discuss computational complexity and intractability. So first, let's get some motivation and notion of intractability. So when faster isn't possible. So your boss asks you for a more efficient algorithm for a problem. You try every known approach. None run in reasonable time. Some problems resist all attempts at polynomial time solutions. The question is the algorithm too slow, or is the problem itself hard? This leads to the field of computational complexity theory. So an algorithm's inefficiency can be fixed, and intractable problems cannot. So an inefficient algorithm is just a poor implementation for an otherwise easy problem. For example, an n-cubed sorting algorithm versus an n log n sorting algorithm. An intractable problem means that there's no polynomial time algorithm that exists, or at least is known. The examples would be traveling salesperson, 0-1 knapsack, or Hamiltonian circuit. An undecidable problem means no algorithm can ever solve all instances. So the complexity is not even a consideration because problem is undecidable. Okay, so an example would be the halting problem, which is the classic example. So what is a polynomial time algorithm? An algorithm is considered polynomial time if the t of n is less than or equal to c, some constant, times n to the power k. And k and c must both be constants for all large n. So you'll notice this makes it a polynomial. We would consider something like constant to still fall under polynomial time. So if it's big O of 1, for example, or linear, right? Those would be also an example, and quadratic, cubic, and anything higher than that, as long as it's a polynomial. So it grows within a polynomial bound, and if the growth is within a polynomial bound, we consider it tractable. So examples would include insertion sort, which is quadratic, merge sort, which is linear arithmetic, and then Dijkstra's algorithm, which is quadratic with respect to the number of vertices. So in contrast, an exponential t of n equals 2 to the n, or factorial. This means that they are called intractable. So no polynomial time algorithm exists, at least that we know of. A rule of thumb is that if the runtime doubles for each extra input bit, it's exponential. So it's like the opposite of just a logarithmic algorithm. So with a logarithmic algorithm, like binary search, you can double the data set size, and it only takes one more basic operation. But with exponential, adding one more piece of data to the data set causes it to double the number of operations. All right, so matrix chain multiplication, the brute force enumerations, mean all parenthesizations that we talked about before, is big O of c to the power, or c sub n. So that is 4 to the power n over n to the power 3 divided by 2. This actually should, I should have fixed that. There we go, fixed it. But this is exponential, so it's 4 to the n over n to the 3 to the power, n to the 3 over 2. With dynamic programming, we can take advantage of optimal substructure and get big theta of n cubed. So it demonstrates that the same problem can be approached exponentially or polynomially. So complexity analysis tells us where the real barrier is. Input size matters. So input size is the number of bits or items describing a problem instance. Always define what n means. Okay, for sorting, it's the number of elements. For integer factorization, it would be the number of bits in n, okay, which is approximately log of n. A problem may appear exponential under one definition, but polynomial under another. An example would be testing primality in n versus in log n. So takeaway is that the complexity classification depends on the input size measure. So the spectrum of problem difficulty from easy to impossible. Again, as an illustration of what we talked about earlier, as a reminder as well, Tractable means polynomial time solvable. So solvable in polynomial time. Sorting, shortest path. Intractable but decidable means exponential or worse but solvable, at least in theory. So, for example, the traveling salesperson problem or the knapsack problem. 0, 1 knapsack. So undecidable means no algorithm exists. So the halting problem, it just doesn't exist. It doesn't matter how much time you have in the universe or how fast an algorithm is, there is no algorithm to solve it. Motivation, summary, and term. So intractability means no known polynomial time algorithm exists. Distinguish algorithm inefficiency from inherent problem hardness. We want to do that. Polynomial time means efficiently solvable, at least in theory. Input size definitions matter as well. And the study of complexity leads naturally to the P versus NP question. So let's revisit input size. So why does input size actually matter? So every complexity expression, T of n, depends on what n means. For numeric problems, n is not the number's value n, instead the number of bits required to represent n, or number of elements in an array, or something like that. The same algorithm can appear polynomial or exponential depending on that definition. Precise definition of input size is essential for correct complexity classification. The key question is, what is n in this problem? Sorting versus arithmetic. So always express runtime relative to the data's encoding length. So sorting n numbers, the natural input size is n equals the number of elements. Typical complexity would be linearithmic, so that's polynomial. Multiplying two k-bit integers, n equals k, which is the bits per operand. So classical would be big theta of k squared. The Karatsuba algorithm definition is the theta of k to the 1.585. That's also polynomial, right? Both of those are polynomial. So enumerating all subsets of n items. So n equals the number of items, that's big theta of 2 to the n. So that's inherently, that problem is exponential. So let's look at primality testing. So the naive test is try all divisors up to the square root of n. So that's big O of the square root of n operations. If input size is the number of bits, that's approximately log base 2 of n. So then the square root of n is approximately 2 to the power of n divided by 2. That is exponential in n. But modern AKS primality testing that was discovered in 2002 is big O of n to the 6. That's polynomial. Okay, it can still be very slow practically, but it's polynomial. All right, so changing encoding can change measured complexity. Unary representation, the value n takes O to the n symbols. A binary representation, it's O to the log of n symbols. So an algorithm that is big O of n squared for unary input becomes big O of 2 to the 2n for binary input, which is exponential. Real-world complexity uses the most compact reasonable encoding, which is usually binary. So input size summary. Input size determines the scaling behavior of T of n. For numerical problems, we use bit length, log n, as n. A change in encoding can reclassify an algorithm's complexity. Understanding input size is vital before deciding if a problem is tractable or intractable. All right, so some general categories of problems. From algorithms to problem classes. So we now shift focus from individual algorithms to entire problems. Why? Some problems are easy no matter the approach. Others are hopelessly hard. The goal is that we categorize problems by their inherent computational difficulty. Three broad classes emerge, as we've discussed before. The polynomial time solvable, which is P, intractable but decidable, meaning theoretically you could solve it, and undecidable, which means you absolutely cannot solve it, period, no matter how much time you had. So category 1, polynomial time solvable, means that the problems are solvable in polynomial time. These are considered tractable, reasonably efficient even for large inputs. Examples: sorting, big O of n log n; matrix multiplication, big O of n cubed, even the basic straightforward multiplication algorithm; Dijkstra's shortest path, big O of v to the v squared, or big O of e log v. And set P means all decision problems solvable in polynomial time. So this is a set, the data structure set. All right, so category 2 is intractable. So problems we can solve exactly, but only in exponential or worse time, means the computation time grows too fast to be practical, at least for large n. So examples are 0-1 knapsack, traveling salesman problem, or traveling salesperson problem, a graph coloring, subset sum, and Hamiltonian circuit, which is also heavily related to traveling salesperson. Still decidable, so eventually finish or for finite input. Even if it took 1,000,000 years, it would still be theoretically solvable. The key point is that intractable doesn't mean unsolvable. Intractable just means they are impractical for large values of n. Category 3 are undecidable problems. Okay, this means that no algorithm can solve all instances ever. This was proven by Alan Turing in 1936 when he was experimenting with the Entscheidungsproblem, which was something David Hilbert proposed. And this turned into his description of the halting problem. So other examples, program equivalence. Do two programs always produce the same output? And the post-correspondence problem is another example. They exist beyond the boundary of algorithmic computation. And then just the examples in context right here. Summary on slide 21. All right, so as a summary, polynomial time means they're tractable, feasible in practice. Exponential time are intractable, solvable but impractical. Undecidable means no algorithm is possible to solve them. No matter how hard you work, no matter how much time you have to run an algorithm, you can't find an algorithm that will solve them. So these categories form the foundation for understanding P, NP, and NP-complete classes. So we get to the theory of NP. You've probably seen this before, hopefully. We now ask, how do we formally describe easy versus hard? And the field defines two foundational sets, P and NP. These describe typically decision problems, which are problems with yes or no answers, true or false, yes, no, on, off, things like that. Understanding them allows us to compare problem difficulty. And it leads to one of computer science's most famous open questions. Is P equal to NP? We've not proven it one way or the other. It's one of the Millennium Prize problems, and if anyone solves it, they get $1 million effectively. So the set P, polynomial time, the definition is that all decision problems solvable by a deterministic Turing machine in polynomial time. Informally, we would say problems that could be solved efficiently. Examples are sorting problem, searching problem, shortest path, minimum spanning tree. They are all polynomial. They're the set P. They can be solved in polynomial time. If an algorithm's worst case runtime is less than or equal to c times n to the k, it's n the set P. And symbolically, we would say P is the set L such that L is decidable in polynomial time. The set NP is non-deterministic polynomial time. Now, what this means is all decision problems whose solutions can be verified in polynomial time. You can think easy to check, but possibly hard to find. Okay, easy to verify, possibly hard to find. Every P problem is also in the set NP. These are two different sets, but P is always a subset of NP. We know that to be true. We know that P is a subset at a minimum of NP. Because solving, if you are able to solve it in polynomial time, you can definitely verify it in polynomial time. But there are some things like Hamiltonian circuit, which are intractable. They're not solvable in polynomial time, but they are verifiable in polynomial time. If I give you just a set of nodes in a particular order in a graph and say, is this a Hamiltonian circuit? You can go through them and verify it's a Hamiltonian circuit in polynomial time. But actually finding the Hamiltonian circuit, you can't. We don't know of any algorithm that can do that. So solving is at least as hard as verifying. So it's unknown whether NP is just a proper subset of P or if NP is equal to P. So examples of this, NP, are subset sum, graph coloring, Hamiltonian circuit, TSP, decision form. So you can verify these things, but not necessarily solve them in polynomial time. So subset sum problem, just as an example, is given a set of S, or set S of n integers in a target T, does any subset of S sum to T? Brute force, you would do 2 to the n subsets, and that's exponential. The verification, though, is pretty easy. Given a subset S prime, just add those numbers and compare, and that only takes linear time, so it's definitely within polynomial. Conclusion is that the subset sum problem is NP because solutions can be checked in polynomial time. We don't know of a polynomial solution, just the verification. And this should have a different title. This should say P versus NP right there. So this is an Euler diagram from our friend Wikipedia, and this is showing us these are the possibilities. We don't know which one's which, but if P is not equal to NP, then NP consists of all polynomial, of course, and it also has some NP complete, but those are also all NP hard, but there's also NP hard problems that aren't NP complete. But if P is equal to NP, it would also be equal to NP complete if P is equal to NP. This is the other possibility. Now, most computer scientists, not all, but most think the one on the left is true. I'm included in that. I think that P is not equal to NP because I figure someone probably would have solved it by now or come up with a polynomial algorithm by now to solve an NP complete problem, but no one has. So the NP complete are the hardest of the NP problems, and if you can solve even one of these in polynomial time, you will prove that P equals NP. No one's done it yet. So NP complete problems are a subset of NP representing the hardest of the NP problems. A problem C is NP complete if it's in NP and every problem within, or that's an element in NP, can be reduced to C in polynomial time. It means every single problem in can be reduced to an NP complete problem. So if any NP complete problem has a polynomial time solution, then all NP problems do. So that would prove that P equals NP. Cook's theorem is that the SAT, for example, is NP complete. That was the first proof related to NP complete problems. Okay, so polynomial time reduction. What is a reduction? It's when you convert one problem's instance A into another problem B in polynomial time. So that A is yes if and only if B is yes. Now I should say if it's a polynomial time reduction is if it's in polynomial time. A reduction in general would just be if you can convert one into another. But the conversion is basically a mapping process. So the notation is that A less than or equal to sub P of B if it's polynomially time reducible. It's very common for mathematicians to try to, if they have a problem they already understand and know something about, then it's very, very common for them to want to map another problem to it. Instead of finding a direct solution right away, they can map one problem to the other, and that tells them that if you can solve the one that you already know how to solve, you can solve the other one. Used to prove hardness. So if A is hard and A is less than or equal to P of B, reducible to B, that means that B is at least as hard as A. Okay? So example chain would be SAT, 3-sat, click, vertex covering, TSP decision problem. So NP hard, easy, NP equivalent. Some of these are much rarer to hear about, but NP hard, at least as hard as every NP problem. Is it in NP? Well, not necessarily. Some of them are. The NP complete problems are NP hard and NP. Example, optimization TSP, knapsack max value problem. NP easy means every NP problem reduces to it, meaning upper bound notation. NP easy is less commonly discussed, but it sits symmetrically to NP hard. It may be NP or not. Certain verification tasks go into that. NP equivalent means if it's both NP hard and NP easy. So optimization, decision versions. Another example, TSP decision versus optimization. The decision is there a tour less than or equal to k units? And that's in NP. You can verify the distance. TSP optimization is find the shortest tour. That's NP hard. It's not in NP. We don't know of any algorithm at all that would be capable of solving, getting a shortest tour in polynomial time. So the decision and optimization versions are polynomially equivalent, used widely in logistics, circuit design, and AI planning. All right, so as a summary, P means problems solvable in polynomial time. NP are problems whose solutions can be verified in polynomial time. NP complete are the hardest subset of NP problems. NP hard means at least as hard as NP, but may not even be verifiable in polynomial time, let alone solvable. Reduction is a key tool to relate to problem difficulty. And if one NP complete problem is solved efficiently, then all of them are, and we will have proven P equals NP. Handling NP hard problems. So when exact solutions are just impractical, NP hard problems likely have no polynomial time exact solution, but they still matter in logistics, AI planning, network design, and scheduling. So the goal is that we want to find practically useful methods that trade perfection for feasibility. So we're sometimes willing to have suboptimal solutions. 4 broad strategies are exhaustive search with pruning, heuristics and meta-heuristics, restricting the problem scope, and approximation algorithms that don't give you an exact solution. So strategy 1, backtracking and branch and bound, systematically explore possible solutions but prune unpromising branches. So backtracking, again, depth first search through the solution space, abandon branch as soon as constraints are violated, and classic examples are n-queens, graph coloring. Branch and bound are keep the best known cost, that's the bound, skip subproblems whose lower bound is greater than or equal to the current best. An example would be a branch and bound solution to the traveling salesperson problem. Okay, how to do this would be start with the initial tour, cost equals C sub 0. Generate partial tours and compute lower bounds using minimum spanning tree or greedy estimates. If the bound's greater than or equal to C sub 0, you prune it. Otherwise, expand and update the cost. So in effect, you get a dramatic reduction in explored nodes, still exponential in the worst case, but tractable for many examples. Okay, so the legend, each node is a partial tour. Number in the parentheses is the lower bound estimate. X is pruned, star is a complete valid tour. And in some cases, you would get a suboptimal solution, but it might be good. Okay, heuristic and meta-heuristics provide good enough solutions quickly with no optimality guarantee. Common approaches are greedy heuristics, build locally best choices like nearest neighbor, TSP. Hill climbing, simulated annealing. These are cool little techniques that are used in things like machine learning. Explore, then accept better or occasionally worse solutions. Genetic algorithms, another fun AI approach, is take the population of solutions, do selection, mutation, evolution, and they converge. TSP, traveling salesperson problem, can be solved with this, and so can many other problems. Valuable for real-time and large-scale systems. An example, again, nearest neighbor TSP produces the tour within 25% of optimality for many cities. Strategy 3 is just restrict the problem scope. So some subclasses of NP hard problems become tractable when restricted. So for examples, for the knapsack problem, if weights are small integers, pseudo-polynomial dynamic programming solution, big O of n times W. Bayesian networks, singly connected, like topology is the tree, has a polynomial time inference. The Boolean satisfiability problem, 2sat is solvable in big O of n plus m, 3sat is NP completes, though. The insight is that the structure and constraints can shift a problem from intractable to tractable, depending, obviously, on those structure and constraints. Strategy 4 would be approximation algorithms. So polynomial time algorithms that guarantee a result within a known factor of the optimum. Common for optimization versions of NP hard problems. So an example, TSP with triangle inequality. Compute the minimum spanning tree, traverse it in pre-order, and the tour less than or equal to 2 times the optimal. Okay, so it might be twice as long as the optimal, but it's probably better than many other tours. Bin packing, first fit decreasing uses, less than or equal to 11/9 of the optimal plus 1 bins. Approximation ratio R, algorithm guarantees A of S less than or equal to R times the optimal of the set. And here's just a visual comparison on slide 42. Summary of handling NP-hard problems. So NP-hard problems define a frontier of computational feasibility. Strategies include prune the search space, backtracking, branch and bound, etc. Use heuristics to get good solutions fast. Limit the problem domain to tractable cases. Apply approximation algorithms with performance guarantees. So even when P is not equal to NP, we can still solve important instances effectively. All right, summary of this week's content are that tractable means polynomial time solvable and thus practically feasible. Intractable means NP hard or NP complete, no known polynomial algorithm. Undecidable means no algorithm exists for all instances. P is a subset of NP, but P equals NP remains unknown. We don't know if it's equal or if it's a proper subset. Reductions connect problems and define relative difficulty. So computational complexity classifies problems, not just algorithms. The polynomial time is the benchmark for feasibility. NP completeness reveals shared hardness across many domains. Practical computing focus is approximation, heuristics, and domain structure. The open question is that is P equal to NP? This still defines the frontier of computer science. And of course, we just have a summary with a table here showing that we have some alternatives and options, but we don't have a polynomial solution for everything. So that's what I have for you this week. If you have any questions, please let me know. Thanks a lot. Bye-bye.